Okay, great. Welcome back, everybody, to the fourth N3AS seminar of the semester. Today, we are absolutely delighted to have Anna Franckowiak here from Ruhr University Bochum to talk to us about multi-messenger astronomy with IceCube. So Anna, please, whenever you're ready, we're very happy to hear your talk.
Hi everyone, thanks for having me. I'm having a little bit of a cold, so I hope I manage to talk for 30 minutes today. My understanding is that most of you are in Berkeley. Actually, I used to live on the other side of the bay, and I have to confess that I do miss it a lot. Yeah, today I will tell you a bit more about multi-messenger astronomy with high-energy neutrinos. So the main reason we look for high-energy neutrinos is to solve the more than 100-year-old mystery of the origin of high-energy cosmic rays. You all know that high-energy cosmic rays bombard us from all directions all the time, and they reach incredible high energies, 10 million times larger than what we can reach with the LHC at CERN. However, the problem by figuring out where they're coming from is that they are charged particles. So on the way from the source to us, they will be deflected by magnetic fields and they do not point back to the origin anymore. And this is now where the high energy neutrinos enter the game, because they would be produced in interactions of those high energy cosmic rays with ambient matter or photon fields. And then the neutrinos are neutral particles, so they travel straight. And when we manage to detect them and reconstruct their direction, it means they do point back to the side of hadronic acceleration. So once we have the neutrinos, we know the direction where we want to look at, but now we also need photons to tell us what is actually in that direction, what kind of source is there that is able to accelerate particles to those incredible high energies. So neutrinos are amazing messengers from the high energy universe, but at the same time, they're also really difficult to detect. As all of you know, IceCube is the largest currently operating neutrino telescope. It's located in Antarctica, close to the geographic South Pole. And here you see a sketch. So it's actually a cubic kilometer of very clear ice instrumented with optical modules. A little bit more than 5,000 optical modules, and they attached on 86 strings that are cables 2.5 kilometers in the ice, and the bottom kilometer is instrumented with the optical modules. So we have a grid of optical modules that's instrumenting a cubic kilometer of ice. And this is how it looks like when we catch one of those very rare neutrino interactions. We distinguish between shower events and track events. The track events we get from muon neutrinos that do a charge count interaction. So we produce a muon, and the muon makes a nice long track through the detector. And you can see this here. And each of the little dots you see is one of the optical modules that was hit by Cherenkov photons produced by the muon traveling through the ice. And different colors indicate different arrival time, and different sizes of the blobs indicate different amounts of light measured by this module. And then we have another signature. We call this shower events. We get them from neutral count interactions or charged count interactions of electron or tau neutrinos. In that case, we get a shower that has some extension, but the extension is small compared to the distance in our instrumentation. So we more or less see a spherical Cherenkov light signature. It's very hard to reconstruct the direction of this. However, it's useful to reconstruct the energy, because most of the light will be inside the detector, and that's a good measure for the energy, while the muon can be produced outside of the detector, so it's more difficult to get a good energy estimate. However, in my talk today, I will focus on trying to do astronomy with neutrinos. So a decent angular resolution is important. So I will focus on the muon events. With IceCube, of course, we do a lot of different, we cover a lot of different science topics, and an overview is shown here. And today I will mainly talk about multi-messenger astronomy. So only a tiny part of what we can do with IceCube. So keep that in mind. The breakthrough in high energy neutrino astronomy happened in 2013 when IceCube first discovered a diffuse flux of high energy neutrinos. And the measurement is shown here. The two different colors are just two different detection channels, and the diffuse neutrino flux is here compared to the diffuse gamma ray flux measured by the Fermi Gamma Ray Space Telescope, and in green with the ultra high energy cosmic ray flux measured by the Auger Observatory. And in this representation, you see that the three fluxes are more or less on the same level, and that tells us that a similar amount of energy is injected into those three different messengers, which maybe tells us that they are connected. However, we don't know where the ultra high energy cosmic rays come from. We still don't really know where the high energy neutrinos come from, and we have a pretty good idea where the gamma ray background comes from. That is dominated by gamma ray blazars. Blazars are active galactic nuclei with the jet pointing in our direction, and those dominate the gamma ray sky. So how can we figure out now where those neutrinos are actually coming from? So the first naive thing to do is to look at a sky map of neutrinos. And in this sky map, you see only neutrinos at quite a high energy threshold, above 30 TeV. And at that energy threshold, roughly half of the event are actually cosmic neutrinos, and the other half would be atmospheric background. And the sky map is in equatorial coordinates. So this gray line that you see here would be the galactic plane. And what you see in the sky map, or better, what you do not see in the sky map, is a strong clustering along the galactic plane. I mean, you don't see it by eye, but also our more sophisticated algorithms looking for clustering along the galactic plane so far didn't find a significant excess. And the second thing you do not see is strong clustering in a certain direction. So obviously we're not dealing with a handful of very strong neutrino sources, but we're dealing with a lot of dim neutrino sources. Okay, probably each of those events here is a neutrino source in itself. So the map, the neutrino sky map, is compatible with an isotropic distribution. And since we don't see strong clustering along the galactic plane, most of the neutrinos in the diffuse flux have to be of extragalactic origin. So at this point, the neutrinos themselves don't tell us yet where they're coming from. And to figure out where they're coming from, IceCube has set up a so-called target of opportunity program. And the goal here is to identify the sources of the high energy neutrinos by finding an electromagnetic counterpart to the neutrinos. And the idea is that with IceCube at the South Pole, we can now identify interesting high energy neutrino events in real time and reconstruct the direction, and then broadcast this information to a network of telescopes around the globe. And then those telescopes ideally would immediately point in the direction where the neutrino was coming from, trying to identify an electromagnetic counterpart. So when I say interesting events, we're looking for a single high energy muon track events, roughly above 100 TeV energies. By applying such a selection, we end up with our so-called gold stream. So the highest quality events then we can select is roughly 10 per year, and half of them we expect to be of cosmic origin, while there's still 50% atmospheric background contamination in this stream. We can select and reconstruct their direction at the South Pole with a median latency of only 30 seconds, and until we can actually notify the telescopes that then could look in that direction. So why are we doing this in real time? Most of the neutrino source candidates are of a transient nature, or they're variable. So with this program, we increase our sensitivity to identify potential counterparts that are transient and variable. Because if we then wait a year and look in our data after a year, then probably the counterpart will have faded. So it's important to observe the counterpart quickly to really cover all the possible sources. This program is in place since April 2016. Since April 2016, we sent alerts to the to the public. And I want to highlight one very interesting event, a high energy neutrino, almost 300 TeV energy that we detected in September 2017. And this is the event display. And here you see an animation of this event display. So there is a little bit of noise in the detector, and then eventually the muon enters, and you can really nicely see the long track of the muon going all the way through the detector. So this is a pretty nice muon track event. We could reconstruct the direction to 90% uncertainty region of the sky covering 1 square degree. But the neutrino by itself, you could argue, is not very interesting because it had a so-called signalness of 56%. That means the probability that this was a cosmic neutrino is 56%. So there is still almost 50% chance that this is an atmospheric background event. But now if we combine this with electromagnetic data, it actually becomes very interesting. And what you see here in this little movie is the gamma ray sky in GeV energies measured by the Fermi Gamma Ray Space Telescope. And each image in this movie is 1 week of data subtracted from an average sky map. So what you see plopping up here are variations in the sky. So you see there's a lot going on in the gamma ray sky. If you look carefully, you can even see the sun moving through. And then starting from April 2016, you see the high energy neutrino alerts overlaid in this map. And then in September 2017, we received this 300 TeV event where I just showed you the event display. And now if we zoom in, we see that this neutrino is right on top of one of the gamma ray flares in the Fermi sky map. So we can take a closer look at this gamma ray flare. It was actually produced by an already known gamma ray source, the blazar TXS0506. So again, a blazar is an active galactic nuclei with a jet pointing in our direction. And those dominate the gamma ray sky. Thanks to the survey that Fermi has been doing for, at that time, almost 10 years, we have a nice archival light curve, and you see that here in days relative to the arrival of the high energy neutrino. So at 0, we have the arrival of the high energy neutrino, and this is the gamma ray light curve. So you see in the past, there was some variation, but really the largest flare that this source ever made was at the time where the neutrino arrived. The source by itself is interesting. It's among the 50 brightest gamma ray blazars in the Fermi catalog. And that means it's in the top 3% of the bright gamma ray blazars. So it was seen by Fermi in GeV gamma rays, and that was, of course, announced by Fermi. So this started a large multi-wavelength observing campaign of this source. And it was then also detected for the first time in very high energy gamma rays with the magic Cherenkov telescopes. You see them here in La Palma. They detected for the first time the source at energies higher than 100 GeV. Here you see the magic significance map, and those lines here are the neutrino uncertainty 50 and 90% uncertainty region. You see that the source is really right in the center, very close to the best fit neutrino direction. So now, of course, you have to ask the question, how likely is something like that happening just by chance? Like randomly, you look somewhere in the sky, you look at a 1 square degree area in the sky, how likely would you find a flaring gamma ray blazar in such an area? And it's actually not very likely that you find such a bright gamma ray blazar in 1 square degree in the sky. We carefully did this calculation. We also included trials because this program was already running for a few years. And we find that the significance of this association is at the 3 sigma level. I know for particle physicists, that's probably not enough. We wouldn't call this a detection, but this is the most significant source candidate that we have ever identified in high energy neutrino astronomy. So obviously we're quite excited about the source. So if we now believe that really that was the source that produced the 300 TeV neutrino, then this tells us that there have to be protons accelerated in the source to energies of at least a few PeV in order that, in order for those protons to interact and produce a neutrino at 300 TeV energy. So this would be the first extragalactic PeV proton accelerator that we can directly identify thanks to the neutrino measurement, which is pretty cool. Now the question is, does that solve our question? Where do the neutrinos come from? Does it mean that all the diffuse neutrinos that we detect with IceCube are all of them produced by gamma ray blazars? And the answer is probably not, because we have performed a dedicated study where now we take all of the gamma ray blazars that Fermi detects, and now we look for neutrinos only from those positions. So we try to find a signal from the entire population. So this is a study using 3 years of IceCube data and more than 800 blazars detected by Fermi. And we try to find an excess from the position of those blazars, and no excess was found. And that allows us now to set an upper limit to the contribution of blazars to the diffuse neutrino flux. And the result is shown down here. This plot is a bit busy, so the gray shaded region here is the measured diffuse neutrino flux. And if we now assume that the blazars produce neutrinos following the same spectral shape, then we would get the upper limit that we would get would be this red line here. So that would tell us that only a small fraction of the diffuse flux could really come from those gamma ray blazars. However, if we now assume a different spectral shape, that the neutrinos would follow emitted by the blazars, for example, a harder spectrum, as this one shown here in blue or green, then we can actually explain all of the neutrinos at high energies, but we cannot explain the low energy neutrinos. So in this case, maybe we actually dealing with two source populations, the gamma ray blazars that produce neutrinos at high energies, and then at lower energies, we need a second population that is producing the lower energy neutrinos. And there are many candidates that the theorists suggest that could be high energy neutrino emitters. And I want to focus on one interesting source candidate here, and those are tidal disruption events. So you get a tidal disruption event if a star is approaching too close to a supermassive black hole. So if the star gets too close, eventually the tidal forces get larger than the gravity holding the star together. And in that case, you would rip apart the star, and part of the debris would form an accretion disk around the black hole. And in some rare cases, you would also produce a relativistic particle jet. So you could say maybe it is similar to an AGN, but just on a shorter time scale. Today we have maybe 50 to 100 of those tidal disruption events identified. Only 3 of them have a confirmed relativistic jet. And thanks to modern optical survey instruments, the number of TDEs increased to this 50 to 100 candidates over the last years. And one of the key players in detecting tidal disruption events is the Zwicky Transient Facility, located in California at Mount Palomar. And you see the dome of the instrument here. And what is special about ZTF is that it has a giant field of view. It has a very large camera, and therefore has a very large field of view. You see this here actually to scale compared to other large telescopes, and the ZTF field of view covers 47 square degrees of the sky. So for comparison, the whole sky is 40,000 square degrees. And you see the moon and Andromeda here to scale. So it's actually covering 250 times the full moon with one single pointing. So that allows ZTF to basically do a survey of the visible northern sky almost every night. So how do we use ZTF to try to detect neutrino counterparts? We receive the high energy neutrino alerts that IceCube sends out. We then observe them with ZTF to get deeper observations, ideally as close as possible to the arrival time of the high energy neutrino. And then, yeah, normally we cover a large footprint because the angular reconstruction of the neutrinos is not great. So it could be a few square degrees that we have to cover. And then usually we always find a lot of variable objects or transient objects in a few square degrees. So we developed a software package that allows us now to identify the interesting transient and variable objects in the sky. So we get rid of stars, planets. There's always a few subtraction artifacts left in the images, and asteroids. Obviously, we're not interested in because we don't think that those could produce high energy neutrinos. Then we usually left with a handful of potentially interesting sources, and those then we schedule for additional follow-up with other wavelengths or for spectroscopy to really classify the source, and that allows us to reject other unrelated transient, for example, type 1a supernova. They're very common in the sky, but they're not believed to be high energy neutrino emitters. So thanks to this program, we identified an interesting counterpart to a neutrino that we detected in October 2019. It had 200 TeV energy, and I should say that this work was led by my student Robert Stein, who is now lucky as you are. He's now a postdoc at Caltech, enjoying the sun of California. So yeah, Robert scheduled ZTF observations in the night after the neutrino arrival. We got 2 observations here in 2 different filters, and another one in the next night. Here you see a cutout of the image, and the variable or the transient source that we find is right in the center of a galaxy. Then I told you ZTF has this large field of view and is performing a survey, so we can now go back and look at archival data. And this is the ZTF history of the source. So you see the source was even more active in the past. It actually peaked in the optical 150 days before the neutrino arrived. And of course, that wasn't unnoticed in the ZTF collaboration. They had seen the source rising. They triggered follow-up observations in the UV and also in X-ray. And they also classified the source as a tidal disruption event at a redshift of 0.05. And the name of this tidal disruption event is 2019 DSG, because it's very difficult to say and very hard to remember. We give nicknames to our tidal disruption events, and this one is Bran Stark. So they're all named according to Game of Thrones characters. And I thought it was funny because there's some similarity, I guess, between Robert and Bran. So we benefit from the archival observations, but now you already see here that it seems the ZTF black hole group lost interest in the source. They didn't follow up on the source anymore, but because of the detection of the high energy neutrino, we now became interested in the source again. So we triggered more follow-up observations to see if there was some interesting activity going on at the time of the neutrino arrival. So we were a bit puzzled that actually the neutrino arrived 150 days after the peak in the optical, but we have quite interesting observations in radio that I'm showing you here. So this is not a light curve that shows the frequency. Flux is a function of frequency, and the time behavior is color coded here. So you see in radio, actually the source is getting brighter over time until 120 days, and then eventually it's moving to lower energy. So that tells us that there is some active inner engine that is still powering the source 150 days after the optical peak. So it could be that the optical emission doesn't really follow the accretion that's happening around the black hole. And here you see we calculated the energy injected, and it's actually more or less constant over time. And if that is the case, it is also the probability of the neutrino to be produced would also be constant over time. And then also we went and calculated the chance coincidence. How likely is it to find a tidal disruption event of similar brightness? And we find it's 0.2% to find a TDE at similar brightness or brighter than this Brand-Stark event. Yeah, so that will be the first time we actually associated a neutrino with the tidal disruption event. Many different theory groups now investigated this event and tried to predict whether high-energy neutrino emission could be produced in the source. And there are actually a number of different scenarios that were suggested. For example, the neutrino could be produced in a relativistic jet, in shocks inside this relativistic jet. It could also be produced by a non-relativistic outflow that interacts with the ambient matter. It could be produced in the accretion disk or maybe in the corona around the accretion disk. So with only one neutrino detected from a high energy, from a tidal disruption event, we cannot really distinguish between those scenarios. So we really want to find more of those associations. And I'm very excited to show you that we found a second candidate, a second tidal disruption event associated with another high energy neutrino. This one is called Taiwan. And this work was led by my student Simeon. And here you see a comparison of the light curves. So this is a Brand-Stark event, and the red one is Taiwan. In case of Brand, the neutrino arrived 150 days after the optical peak. In case of Taiwan, the neutrino arrived roughly a year after the optical peak. Here the comparison is shown in terms of luminosity. So Taiwan is much, much more luminous compared to Brand. However, it's also at larger distance. And if you would look at this plot in flux space, then they would be more or less at the same level. So we combined the two sources and then arrive at a p-value of roughly 3.4 sigma for those two sources. So that's another indication that actually now TDEs are emerging as a potential new neutrino source class. And yeah, finally, I'm very happy to show you that we have a third event. This was identified by our collaborator, Short van Velzen. So what he did was to not only look at identified tidal disruption events, but he looked at a larger sample of accretion flare events. And I don't want to go into detail. You can ask me later how he identified those sources, but it's a larger sample that would also include the TDE candidates. And he finds a third source that is called Lenzel. You see the optical light curve here. So it looks pretty similar to other tidal disruption event candidates. And also here, the neutrino arrived with a delay of roughly 150 days. So Short suggests that this could be a unified population of accretion flare events producing those high energy neutrinos. And now with those three events, we reach a significance of 3.7 sigma. So it's getting more exciting. So we really want to look for more of those candidates, and we're planning now to look at archival neutrino data detected with IceCube to hopefully confirm this hypothesis that really those accretion flares are powerful neutrino sources. So we found this more or less empirically, and it's actually it's very interesting because those three events together could actually produce a significant fraction of the IceCube diffuse neutrino flux. Short calculated this to a level of 20% of the diffuse flux, however, with quite large uncertainties because we only have three events to look at here. But that's actually quite surprising because we know that AGNs are actually, they're much more luminous, so they inject much more energy into the universe. So why should the neutrino emission be dominated by tidal disruption events, while in the electromagnetic, the AGNs outshine the tidal disruption events by 2 orders of magnitude. And the hypothesis that we have here is that the tidal disruption events and also those extreme accretion flares, they are very close to the Eddington limit, right? Regular AGNs would be quite far away from the Eddington limit. So maybe close to the Eddington limit, there's some process that allows very efficient cosmic ray acceleration and neutrino production. So that's basically the hypothesis. They could be very efficient neutrino production in tidal disruption events that is somehow different from regular AGNs. And that's the hypothesis we're going to test with more IceCube data. And So be excited. You can be excited for future results you will see from us from those type of events. Before I conclude, I want to mention that, of course, we're working on building larger new neutrino detectors. There's the KM3net being under construction in the Mediterranean, and Baikal GVD under construction in Lake Baikal in Russia. Both of them will also be on a cubic kilometer scale. And at the South Pole, we're planning IceCube Gen 2 that will have a 5 times increased sensitivity to neutrinos in the TeV to PeV range. So it would have almost a 10 times bigger volume in ice, and would then also be paired with a surface array of radio antennas that are crucial really to reach very high energies. So this instrument is in the planning phase right now, but yeah, would be really exciting to have detectors in different hemispheres, because they would actually be complementary and give us really the best sensitivity in all of the sky. So I hope I could convince you that in this multi-messenger picture, neutrinos are unique messengers from the high energy universe, because they have this connection to cosmic rays and might actually be the key to reveal the sources of high energy cosmic rays. I showed you that the sources are still unknown, but detecting the electromagnetic counterpart is crucial to identify the sources. And I showed you that we have a few first compelling, interesting candidates. That's the Blazar TXS of 506, and then several tidal disruption event candidates that are potential neutrino emitters. So stay tuned for new results that we will show in the future. Thank you very much.
Okay, great. Yeah, thank you, Anna, for this really lovely talk, and congratulations on the observation and identification of these fantastically interesting events. Of course, please join me in a digital round of applause here. Okay, so do we have questions for Anna then? Okay, I see Yong's hand. Why don't you go ahead?
Yeah, hi. Very nice talk. I would like to understand the real kind of observational evidence for this tidal disruption effect correlation. Is it just purely positional plus some time window for search?
Yes. So so what we have to consider is how much of the sky do we cover? And how likely, or what is the rate of tidal disruption events that an instrument like ZTF would detect? And then by calculating how much of the sky did you cover, you can calculate the chance coincidence. And of course, you also have to define a time window to call something a coincidence. And here we assume something like a year. So yeah, as long as ZTF would be able to detect the tidal disruption event, which is usually around 1 year.
Very nice. So this is basically statistical empirical evidence for that. And what's more interesting would be some real mechanism for producing the kind of high energy neutrino you would see with the environment of the tidal disruption event, right? Are there any kind of interesting models people already proposed? Yeah,
so even before we started to look into this, there were people suggesting that tidal disruption events could be cosmic ray sources. And in the recent years, there were several papers from different theory groups predicting tidal disruption events as neutrino sources. So this got us motivated to actually look for them. And after we found the first candidate, there were a bunch of papers really trying to model the emission, where actually could it be produced in the source, and how many neutrinos would you actually expect.
Is this, again, there's an efficiency thing you mentioned at the end, right? The efficiency for producing neutrinos in this particular type of events, the tidal disruption thing. So
yeah, so the different models are those, right?
Yep.
But it's not really clear, because the mechanism seems similar to what happens in a regular AGN, right? And we know that there's a lot of AGNs out there, and they constantly emit, right? And the tidal disruption events, they're rare compared to AGN, and they emit only for a short time. So why should they emit more neutrinos compared to the AGN? So maybe there is really something special about the mechanism in the TDEs that is different to the AGNs.
But there's no real kind of features identified why that particular environment is particularly efficient.
Exactly, we don't really know that. What could happen is that, so one thing you need for the neutrino production is usually in the AGN they call this baryonic loading. So how many baryons you have in the jet, and that could be higher, for example, in the TDEs, because you just like ripped apart an entire star, right? Maybe that gives you more baryons. Maybe that makes it more efficient compared to the AGN. But now with 3 sources, I think we can really start looking into the difference and get a better understanding of what really could make those sources special compared to the regular AGN.
Okay, thank you very much.
Great, and it looks like the next hand I see here is Anna's. Anna, why don't you go ahead?
Hi, thank you very much for the nice talk. I wanted to ask if you also maybe have the data for the other 2 candidates from the tidal disruption event in radio, or is this only for the one of them?
So all 3 of them were also detected in X-ray, and they also feigned radio sources. We don't have this like super nice radio data for the other sources, but there are weak radio detections also for the other sources, which is also interesting because not all of the tidal disruption events are detected in radio. And that's, I guess, another indication that there is particle acceleration going on in the source, because you see the radio emission.
Okay, but so the peak, like the neutrinos were detected at very different times from the peak if you compare to the just light, not radio. But can you also see that the peaks in the radio shift, or are they within similar distance in time?
Yeah, we don't have the same level of radio data for the other sources, unfortunately. So the last source I showed you, Lenzel, was actually found in archival data. So it was, I mean, kind of too late to get radio data at the same time, but there is a like radio source in that direction. So there is some radio emission coming from the source. And for Taiwan, we triggered radio observation and we detected the source, but it's not really clear what if we see a strong time evolution in the source.
Okay.
So it's
yeah. Sorry.
Okay, looks like the next question goes to Sanjay.
Yeah, thanks for the interesting talk. My question is maybe related to what Yong asked earlier. For the tidal disruption events, what is known about the source? I mean, what do we know the black hole mass? Do we know anything about the black hole spin from the observations? How are these somehow unique when you compare it to, say, AGNs, where the black hole mass is very large and the environment very different?
Yeah, let me show you. So I have the black hole mass here. Let's see. No, this is just luminosity, but I think here. Yeah, let me show you this. So here you see the black hole mass, and this is all ZTF detected AGN, and up here you see the TDE candidates. What you also see here is the dust echo strength. I didn't talk about this. So the accretion flare population that Short was looking at was identified by looking for strong dust echoes. So you get so if you have a dusty torus around your source, and then you see the optical emission first, and then this emission would heat the dust torus, and then a bit delayed you see then infrared emission coming from the dust torus. So this is what we would call a dust echo. And we found that the first two sources actually had a very strong dust echo. So this motivated Short to look for more of such sources. And it seems actually it's a very good tracer for TDEs actually. So you see all the TDEs candidates here, you see the black hole mass here. And this line here, the Hills mass is above this limit. You wouldn't expect tidal disruption events anymore, because eventually, so the tidal disruption radius has to be outside of the event horizon, right? If it's the other way around, then you would just see the star disappear, but you wouldn't see a tidal disruption event. So yeah, I hope that answers your question.
Yeah,
I think you can see the black hole masses in here.
Yeah.
Okay, great. Do we have any further questions for Anna then? Okay, perhaps I can chime in with a question that, if it sounds naive, that's only because it is. So you talk about trying to understand these tidal disruption events as sources of neutrinos, and of course the scales for one of these events are very different from the scales of, let's say, a black hole neutron star merger that could be observed at the gravitational wave, in the gravitational wave program. But I'm curious to know, perhaps you could talk about what are the morals that one could potentially learn about this mechanism from these, let's say, spiritually quite similar, but the details are grossly quite different systems. Perhaps that question is not terribly well posed.
No, it is a good question. So the sources you mentioned are also potentially good neutrino emitters, or at least the gamma ray bursts have been suggested a long time ago as excellent sources for cosmic ray production and also as neutrino sources. So I think everyone kind of expected that gamma ray bursts would be the first ones we would see in high energy neutrinos, because also the search for neutrinos from gamma ray bursts is easy, I would say, because you know exactly where to look in the sky, and you have this tiny time windows where you look for your neutrino emission that allows you, of course, to suppress the background a lot. And we have done those searches, and we haven't found any correlation of high energy neutrinos with the gamma ray bursts. Actually, we can disfavor them as the main neutrino sources. Well, in terms of the diffuse flux, they can only produce maybe 1% of the diffuse flux, but that doesn't mean they do not produce high energy neutrinos, right? And it could also be that maybe the ones that are really bright in gamma rays might not even be the best ones to produce neutrinos. So we also look for low luminosity gamma ray bursts, or so-called choke jet supernova, where you wouldn't see the gamma ray burst, but you could still see the supernova signature. So in case of this neutron star merger event, we also looked in the neutrino data, but we didn't find anything. And I think it would also have been kind of unlikely, because first of all, I mean, we know there was a jet, but the jet was off axis. And the models predict somehow the more it would be on axis, the more neutrinos we would see. And the other reason was that it was not in a good position in the sky for IceCube to, IceCube wasn't very sensitive in that direction. But yeah, I guess we could if we detect neutrinos from those, we could learn something about jetted events, right? Do you need a jet, or would like a relativistic or a wind and outflow, would that be enough to produce high energy neutrinos?
Okay, great. Yeah, thank you. I appreciate that perspective. Do we have more questions then? Okay, so I will. So let's thank Anna once again for her time and for this very lovely talk. I'm going to stop the recording so that if people have been too shy to ask a question when it's going to be on wax, then perhaps they'll feel more comfortable. So let me do that now.